The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Okay, so I'm going to work through problem number 9 for the Physics 2020 Midterm Exam 2, year 2006. And this problem says a centrifuge rotor has a momentum of inertia of 5 times 10 to the minus 3 kilograms meter squared. And actually, let me go ahead and correct this. This is 5.0 times 10 to the minus 3 kilograms meters squared. Okay? How much energy is required to bring it from rest to 10,000 RPMs, revolutions per minute? Okay, so we're trying to determine how much energy is required to bring it from rest. So we're trying to basically figure out how much work is required. And we know that what information are we given? We're given it has a moment of inertia, so we know that I is equal to 5.0 times 10 to the minus 3 kilograms meters squared. And we know that the initial velocity, okay, omega I, is 0 because it is at rest, so we know it's not moving. And we know that the final velocity is 10,000 RPM. Okay? So this is the information that's given. From this information, are we able to determine how much work is required? If you remember from translational motion, we know that work, capital W, is defined as the change in kinetic energy. All right? And so we know that the change in kinetic energy is defined as the final kinetic energy minus the initial kinetic energy. Okay? And if we were to write this out, we would have 1/2 mv squared final minus 1/2 mv squared initial. So this would be the change in kinetic energy in translational motion. But we're not dealing with translational motion, we're dealing with rotational motion. So we can write the work equation as 1/2. And remember that for rotational motion, when we talk about mass, we're really talking about a moment of inertia. So that's going to be I. And when we talk about velocity, we're talking about the angular velocity, which is omega. And we can substitute that in. All right, so now that our new rotational equation for work is actually this expression here, where we have moment of inertia substituted for mass, and we have angular velocity, omega, substituted in for velocity. All right. Now, we know that our initial velocity is going to be 0, so we know that this whole term is just 0. So that basically our change in kinetic energy is just going to equal to our final kinetic energy, rotational kinetic energy. So we can say that that's equal to, one thing we're going to have to do first is that we're going to have to deal with this angular velocity of 10,000 revolutions per minute. The reason being is if you look at the answers, all your answers are either going to be in joules or kilojoules. Okay, and in order for it to be in joules or kilojoules, you need to have units of seconds in here. So we have to basically convert this angular velocity to radians per second. So we can do that simply by saying that the angular velocity is 10,000 revolutions per minute, and we know that in 1 minute there are 60 seconds, and we know that in 1 revolution there is 2 pi radians. Okay, and when we work this out, this means that our new angular velocity is going to be approximately 1,047.197 radians per second. All right, and so now let's see if we can make some room here. All right, so now we can just substitute this into our equation, where work is going to equal to 1/2 times the moment of inertia, which is 5.0 times 10 to the minus 3 kilograms meters squared, multiplied by our angular velocity, which is 1,047.197 radians per second. All right, and so when you actually work this out, this works out to be 2,741 joules, which is approximately 2.7 kilojoules. Okay, so how did I get 2.7 kilojoules? Well, we know that 2,741 joules. We know that there are 1,000 joules in 1 kilojoule. All right, so simply all you do is move the decimal place over 3 places. So that's just 2.7 kilojoules. And this is the answer. So the trick to this problem is using the concepts that we learned for translational motion and transferring that to rotational motion by using the analogous variables such as angular velocity and moment of inertia rather than mass. And we had our equation for work, which is basically defined as a change in kinetic energy. And as soon as we had that information, we knew that we could basically eliminate this part of the equation because there was no initial angular velocity. So we just simply substituted the information into here. We had to convert our angular velocity to radians per second because our answers were in kilojoules. And after that, it was simply substitution, and we got an answer of 2.7 kilojoules.
The Teaching Center, UF's Learning Support Center. www.teachingcenter.ufl.edu.